Our next special guest has worked with, or continues to work with, MIT in Massachusetts, has taught at Cambridge and Warwick University, the Astrobiologist, which is a super cool job title, almost as cool as Thrill Engineer. Anyway, please welcome to the stage, William Baines.
Okay. Thank you very much, and it's a real pleasure to be here to talk to you a little bit about what science knows and what we can guess about the possibilities for life on other worlds. This is a really futuristic topic, but I'm going to start by going backwards, back to 1961, and to this guy. This is Frank Drake, and in 1961, he was one of the pioneers of SETI, the Search for Extraterrestrial Intelligence, which at the time was considered to be scientifically completely disreputable and a bit of science fiction. And he pulled together a meeting to discuss how this could happen and what the best search strategy might be. And as an agenda for the meeting, he put together this equation, which is called the Drake equation. Looks a bit daunting. It's a very simple in concept. It says, how many civilizations might there be out there in the galaxy that we could detect, we could communicate with? And this was n up at this end. And it's pointed out that you could get an estimate of n by just multiplying together all these other terms. And he did that, and depending on what numbers you put in those other terms, you get a number n that's between 20 and 50 million. So not really tied down very exactly. But his point was not that you can work out the number. His point was that in principle, you can predict what the number is if you know what all these other things are. And this was quite a conceptual breakthrough because it took SETI from being science fiction to being highly speculative science. So this is the various terms in the equation, and this is why he had this huge range of values for n. What they knew in 1961 was stars. All the rest they did not know. Lots of speculation, lots of hypotheses, lots of TV series, but knowledge, they had none. Now, since then, there's been a huge advance in technology, both in astronomy, in astronomical telescopes and detectors, but also in computer modeling of potential systems, of geochemistry, of stellar physics, of biology, of evolution. And that massive advance in technology and knowledge has allowed us to answer 2 of the terms in the Drake equation. We've got some hints on number 3. So the bounds of this, of n, are still vast. But we're starting to edge towards. And what I want to talk to you today is a little bit about the second one, and then why we do or do not know things about the other terms here. So let's talk about planets to start with. You probably know from the many news reports that we have found a shed load of planets. And when I say we, I don't mean me. This isn't what I do. This is a whole bunch of other people more in the astronomy and physics space. This is a summary from about a year ago now from the University of Puerto Rico of the confirmed planets found around other stars. And there are planets close to the star at the top in what's called a hot zone here, far from the star, and in the middle where they might be at the right temperature for life. There are little guys, there are huge giant guys. There's some really exotic stuff in here. There's a planet being characterized that is orbiting so close to the star that it's boiling away into space. In a couple of million years, it won't be there anymore. There's a planet with a ring system around it so huge, both in size and in mass, that if it was around Saturn in our solar system, you could clearly see it in the Earth's night sky. It will be about 4 times as wide as the moon. There's a planet with an orbit that looks like a comet. There's all sorts of exotic stuff. One of the things that I'm going to point out, 2 things, is that there are planets bigger than Earth, but smaller than Neptune, so-called super-Earth planets. There's nothing like that in our solar system. And there are giant planets orbiting far enough from their star to not be cooked, but near enough to be warm. And the moons of those giant planets are potentially habitable worlds in their own right. So there's lots of planets. There are lots of potential environments. How many of those are actually habitable? Well, that's something we don't know. When you hear a press release about a new habitable world being discovered, what people usually mean is this. They have discovered a world around another star that's orbiting in the region distance from the star such that if it's roughly an Earth-like planet, liquid water will occur on the surface of that planet. That's a very restricted definition of habitable. And it doesn't bring a whole lot of other things into account. For example, on Earth, the reason we have liquid water on Earth is partly the temperature, partly the greenhouse gas effect in the atmosphere, but also that we have what's called a temperature inversion in our atmosphere. The temperature goes down as you go up to the top of the troposphere, up to the stratosphere. That's the sort of place that intercontinental jets fly. And then it starts to go up again above that. If you don't have that inversion, water can escape higher up in the atmosphere and then escape into space. And planets without that inversion would tend to lose their water. We need weathering, we need plate tectonics to turn over the contents of the surface of the Earth. Stuff gets trapped down on the Earth all the time, and without plate tectonics, it is likely that that would then get trapped, including water, including carbon, and the surface would be uninhabitable. We need to deliver volatiles, water, and so on to the Earth. There's whole lots of other things that we need to input into a planet in order to make it genuinely habitable. We do not know how to measure those on planets around other stars yet. And then there's the stars itself. This is the TRAPPIST system, which you, I'm sure, will have heard of. There's the hypothesis that E, F, and G in this system are habitable, and they orbit in that habitable zone. But TRAPPIST-1 itself, the star, is a cool red dwarf. There's a big debate at the moment whether planets around cool red dwarfs can be habitable at all because of the characteristics of the star, because of the energy output from the star, its variation over time. So just being in a habitable zone, in this zone where you have liquid water on the surface, in principle, is not enough. But we do know that it is likely that at least some of those planets will have the right plate tectonics, be orbiting the right star, have the right sort of surface weathering and so on to be habitable. So we can be reasonably confident that habitable planets are probably fairly common. How many of them are actually inhabited? That's a much tougher one, and we do not know the answer. And I want to describe why we don't know the answer, and then what we're doing about that. But first, let's step back and say, what do we mean by inhabited? What do we mean by life? Yeah. There is no formal definition of life, and there's probably a good reason for that, a logical reason for that, not least of which we only have one example of life, us. Every form of life on Earth appears to have originated from a common ancestor. So when you have one example of something, you can't really generalize to other examples because you don't have other examples. But from what we can see about life and what we think about living systems as opposed to non-living systems, life sort of described as something like this. It's dynamic, it's chemical, it selects stuff from its environment, matter and energy, it transforms some of that, it rejects the rest, and all that is done under the direction of an internally coded description of that life. It's a bit dry, isn't it? Take an example. Here's an example of some life, and if you fed that life on this material here, this contains energy, this contains carbon molecules, what would it turn into? Now, if that was a fire, if I was told I can't do this as a demonstration, so I'm sorry, I would have done it. If I had a match here, and I struck the match, it would burn like a match. If I then took that match and set fire to this screen, it would burn like a very big piece of plastic. And then shortly after that, I'd be arrested. If fire was a life form, and I took it over here and set fire to the screen, what you'd get is lots of little match fires growing all over here. And then they start to burn the carpet and lots of little match fires. That's not what fire does. But it is what life does. So what happens here is if I eat lots of chips, I don't turn into a potato, I turn into more me. And that is the characteristic of life. Now that says something very profound about what life must do. Something in here must select molecules from here. Throw away the ones it doesn't want. That's why all life forms inevitably will have toilets. And take the ones it does want and turn them into the molecules to make itself up and translate a code to direct it how to do that. And that all has to be done by a molecular machine that is built by that molecular machine. That's really quite tricky, isn't it? And you can guesstimate how big, how complex that molecular machine has to be. Now, the problem with the origin of life is this. We know how to make fairly simple molecules. on a prebiotic Earth, on a planet with no life. There's a big debate about which of these molecules I've illustrated here are realistic to occur on the early Earth, but they're the sort of size that you can imagine might be produced. We also find a few of them on the surface of Titan. We find them in meteorites. We find them in interstellar gas clouds. So this is the stuff that chemistry that is not life could make. And some of these are quite complicated, certainly compared to the two up the top there, which are the most common molecules in the universe, which is helium atom and dihydrogen gas. Is that complicated enough? No. This is 1/3 of the molecular machine in you that makes proteins. It doesn't make DNA, it doesn't make cell membranes, it just makes proteins. This is 1/3 of the eukaryotic ribosome. And that's probably about the minimum size you need for a molecular machine that can take little molecules in, stitch them together, and build itself. The complexity jump between those guys and this is huge. We are confident that that jump can be bridged. We know it was bridged at least once, but we've no idea how that happened. And so we can't say how likely it is to happen again. Okay, but clearly it did happen. Can we deduce something from the fact that we are here? Life is on Earth. Earth was almost certainly uninhabitable about 4.4 billion years ago. We're confident about that because around that time, a planet about the size of Mars hit the proto-Earth. Both planets were completely liquefied. An enormous amount of material was thrown out into orbit and condensed to form the moon. Nothing living survived that. And certainly by 3.5 billion years ago, and possibly 4.1, there was life on Earth. So life arose, and it rose geological terms fairly quickly. Does that mean life is fairly common? It's easy to happen? Well, no, it doesn't. And this is why. This is a very depressing argument, sorry. But imagine we are in a galaxy where life is incredibly rare. Life is spectacularly unlikely. In fact, it's so unlikely there is only one planet in the entire galaxy that contains life. Out of all those habitable planets, only one planet. Here's an exercise for the audience. What is the name of that planet? Earth. Earth. It has to be this planet, because we're here. Okay? If we weren't on the planet that had life, then we wouldn't be on that planet. This is called the weak anthropic principle, and is a real logical annoyance, but it is true. So we can't distinguish. The fact that we're here does not logically distinguish whether we're in this galaxy or in a galaxy teeming with life. And this is why missions to go and try to find life, or the precursors for life, or the conditions for life on other worlds are not merely scientifically fascinating in terms of planet geology and chemistry, but philosophically important in a really deep level. So missions like the Mars Surface Lander, which is trundling around on Mars at the moment, finding spectacular stuff. The Cassini-Huygens mission, the Cassini crashed into Saturn very recently after an incredibly successful mission. This is a sketch for a potential lander on Europa. These things are looking for life because if they find life, that is evidence that life could be more common than just once in a galaxy. Or could it? The problem with that is this. This is a meteorite. This is a meteorite called ALH 84001. Snappy names these astronomers have. And this caused a big furore a few years ago because this meteorite is believed to be derived from Mars. And careful examination of it showed some little structures on it that might have been fossilized microorganisms. Now, subsequent analysis suggests they're not. But if they had been, that would be so exciting because it would be material from Mars with evidence of life. The problem with that is that came from Mars to Earth. So if there was life on Mars and no life on Earth, a rock could go from Mars to Earth and bring life there. And similarly from Earth to Mars. How this gets here is that there's some asteroid or comet impact on Mars. It blows a lot of rocks up. Some of them achieve escape velocity. Some of those enter an orbit that get into Earth's gravitational field. Some of those fall to Earth. The chances of all that happening are small. The chances of it happening fast enough so that the DNA in the organisms there, and the next talk is going to talk about DNA and its longevity, so listen for that one. The chances that the DNA in those organisms survives the trip are small. The rock has to be the right size. Too small, and the organisms inside will get cooked by radiation in its interplanetary space. Too big, and it heats up to melting on re-entry, and you lose all the bugs. Very, very unlikely, but it could happen, and if we find life on Mars, it will be employment for many generations of astrobiologists trying to work out whether it's Earth life on Mars or Mars life on Earth. What we really want to do is find life on a world that could not possibly have been contaminated by our own life. And that is why we look at extrasolar planets, at exoplanets, for evidence of life. And because we can't go there, we have to look remotely, and the way to look at remotely is to look at their spectrum. So this is an example of what we look for. This is an emission spectrum. So along here we have wavelength starting at 2.4 microns. So this is into the infrared. And on this planet, you'd expect a smooth spectrum, but you see actually dips in the spectrum where components of the atmosphere are absorbing infrared light. And because the wavelengths are quite characteristic of the molecules, you can say what molecules are absorbing what. So here we've got water and carbon dioxide. That's a good starting point. We've got methane there. Wow, methane, that's odd. Nitrous oxide. Very difficult to produce nitrous oxide from volcanoes. And over here we have ozone, which is produced from oxygen. So if you've got a planet with oxygen and methane and nitrous oxide in that atmosphere, really hard to explain how that planet could accumulate those things in its atmosphere except by the presence of life. Now, this is not a theoretical example. This is an actual example. Ladies and gentlemen, I'm here to tell you we have detected life. Unfortunately, we detected life on Earth. This was the experiment Carl Sagan did when the Galileo mission was en route to Jupiter. And he thought, let's test this idea that we can find life on a planet by looking at its spectrum. He turned the spacecraft down to look at Earth and collected that spectrum and said, yes, this approach can work. Now, the telescopes they had at the time couldn't possibly have detected the atmospheres on an exoplanet. They couldn't detect exoplanets at all. Future missions will, however, be able to do that. So this is a NASA composite of the missions that are coming up. Hubble, of course, and Spitzer have been out there. Kepler's been out there discovering planets for many years. TESS and the James Webb Space Telescope from NASA and the Cheops telescope from ESA will start to characterize the atmospheres around the largest planets, Jovian-sized planets. If we're incredibly lucky, they might detect hints of life around more Earth-like planets, more habitable planets. That's very unlikely. Probably we'll have to go to WFIRST or Plato or possibly the New World telescopes in order to start seeing those spectral signatures. But there is a timetable. There's a pipeline of these things going through, and we should be able to start answering the question, can we see signs of things that might be life within most of your lifetimes? The problem is this looks at Earth and says, yes, we can detect Earth life. But what if it doesn't like Earth life? And this is something that Professor Sarah Seeger, whose group I work at MIT, and our colleagues have been working on for some time, thinking, how do we detect life when we don't know what it's like? And there are a couple of approaches to this. This illustrates the first one. Let's imagine you have a planet that's completely unlike anything in our solar system. It's a super-size Earth planet. It's a rocky planet, but heavier than Earth, and it's got a hydrogen-dominated atmosphere. How would life extract energy in that environment? Turns out there's a reaction that it can do that. It can take nitrogen and hydrogen and react them to form ammonia, and this will release energy. Interestingly, that will then escape into the atmosphere, and ultraviolet light from the star will break the ammonia back to nitrogen and hydrogen again. So it doesn't run out of nitrogen and hydrogen. And we can do better. We can say, could we detect that ammonia? And this is the calculation you do. We know that life needs energy to survive, to live. Not just to run around, just to sit here metabolizing it all. All you guys are using up energy. I'm using up more. And we know how much energy that reaction produces. And so we can say how much of that reaction must an organism or a gram of life do in order to generate the energy it needs. And then we can turn that round and say, well, if we need this amount of ammonia in the atmosphere to detect, how much life must there be to generate that amount of ammonia? And so we did that, and this is the answer. We looked at the average density of life across the whole of this hypothetical planet, necessary to detect ammonia in its atmosphere at a distance of 10 parsecs. And how much it is depends on the ultraviolet emission from the star, which depends on the star light. It depends precisely how you detect it. Don't really have time to go into the details of that. But with the exception of detecting by transmission and an active M star here, these are small numbers. Okay? Milligrams or micrograms per meter squared averaged over the planet. For comparison, this is my front garden, and the density of life here is between 50 grams per meter squared and about 1,000 for that rose bush, because it's growing up the wall. In the ocean, on Earth, average is between 10 and 50 grams per meter squared. Even over there in the Sakura Desert on the coast of Peru, which is an awful place. I'm sorry if there's anybody here from Peru, but it is. It's just awful. It's dead. But it's not dead. There's still tens of milligrams of living organisms in that soil. If they were using this ammonia reaction to produce ammonia to capture energy, we will be able to detect it at a distance of 10 parsecs. So that is terribly exciting. The only problem is this is one reaction. There are a whole lot of other gases life on Earth produces, and we don't know why. Ideas, but no proof. Here's an example. Here are the halomethanes. So the halomethanes are chemicals with one carbon in the middle and then a chlorine, a bromine, or iodines decorated around it, hydrogens to fill in the valences. And there are 34 possibilities. Life makes 22 of them, not 12. Why? It's just one of those things, you know? Life. Man, what can you say? The most common one produced by life on Earth is this guy. This is methyl chloride. And if there was an Earth-like planet in orbit around a red dwarf star, this is a study that Segura et al. Did, a group over in Washington State, then there would be a spectral difference between the atmospheres of that planet with methyl chloride and the planet without methyl chloride. That's this bit over here. And you could detect methyl chloride in the atmosphere of that planet if you had a big enough telescope. Cool. But why that? Why not methyl bromide? Why not methylene chloride? We don't know. It just is. So what Sarah Seeger and myself and some colleagues have been doing is saying, okay, let's back off. Let's look at every possible gas that life might produce in the atmosphere. And what we're doing is we've got this great graphic from Janusz Szepetowski at the group. We're thinking of just a pipe of all possible molecules that could evaporate from life into an atmosphere and then start to filter them by what might be produced by volcanoes. They're not interesting. What might disintegrate before it escapes from the water? That's not interesting, and so on. We're in the starting process of that chemistry at the moment. It's a really exciting project, and watch this space if you're reading the astrobiology literature. That's gases. What about color? What about the surface? That's what we see when we look at life. We say, look, there's life over there. It's tall and green. So here's a shot from my office at MIT, and two things to take from this. Firstly, what a great view to have from your office, eh? And the second, we can see life here. It's green, but it's not very obvious. Actually, life is not very green, even plant life. You can't see people at all, by the way. People are trace contaminant. They're not interesting. But if you photograph this in the near infrared, this is what it looks like. Isn't that fantastic? Plants are brilliant white. This is taken in summer. That's not frost or snow. That's what plants look like in the near infrared. And if you look at the spectrum, this is the spectrum. This is the reflectance, the scattering of light. So no scattering, complete scattering. And this is wavelength, starting in the visible here. And this is the transition in the infrared. And there's this steep edge in the curve, which is called the red edge, because it's an edge and it's in the red, which is an illustration or the quantitative measure of this scattering of light. Could we look for this on another world? Well, that's even harder than looking at the atmosphere, because you have to actually image the surface. But apart from that, this depends on the plants being sort of like Earth plants. And we've shown that it's very unlikely that the plants on our hydrogen world, for example, would have this red edge at this wavelength. They might have it at another wavelength, but not this wavelength. What does all this mean? Well, it means that just having one sign is not enough. Finding oxygen on a world, that'd be really interesting, but there are models that show you can accumulate oxygen in an atmosphere without life. Finding oxygen and methane, on a world orbiting within this habitable zone, the liquid water zone, we'd be breaking out the bubbly, seriously. But for the real killer shot, you'd have to have oxygen and methane and the red edge and orbits and chemistry. And if we found all of that around the world, then I'd be booking my ticket to Stockholm to pick up my Nobel Prize. Okay. So, how many worlds develop life? We don't know. We genuinely have no idea in terms of knowledge. Lots of speculation, lots of hypotheses, but no knowledge. But within 20 to 30 years, we'll start to get the data that can tell us. What about intelligence? Well, this is a tricky one because, as any school teacher can tell you, detecting genuine intelligence, even in small children, is rather difficult. But I'm going to divide this into two parts. The first is complex life. So here we are. There's complex life around the Earth around us. There are trees, there are mushrooms, there are chimpanzees. And sometime between the origin of life and 3.8, 3.9 billion years ago and the present day, that complex life arose from very simple life. And there are a number of key steps we can map out along the path here. And I'll list some of these in a subsequent slide. But my question here is not what are the key steps, but did those things occur more than once? Because if they did, if on Earth, once you've got life, then you evolve the same thing again and again, the chances are on another world, if you have life, that thing would evolve, providing the world remains habitable for all that time. So, for example, vision, imaging vision. The mammalian eye, the vertebrate eye, is a unique structure. No other organisms ever evolved a vertebrate eye. But many other organisms have evolved imaging vision systems, have evolved eyes. They're structurally different from ours. The eye of the octopus, which sticks this one down here, looks quite similar to a vertebrate eye, but actually is built rather differently from completely different evolutionary origins. Spiders, insects, other mollusks, trilobites, all evolved eyes from different ways, and they evolved them apparently independently. Seeing is a useful thing to do. Evolution's evolved a way to do it many times. We would expect that to evolve in other worlds. Powered flight evolved at least 4 times because flying is a useful thing to be able to do, and once you have a large enough organism to be able to fly, then flight will evolve. So these are functions. This is not about anatomy. The anatomy of the dragonfly and the bat and the pterosaur and the bird and the flying fish are all different. It's about function. So Dirk Schultz-McCook and I, in what was going to be a little 1,000-word essay, and there's already over 30,000 words of paper, went through all the major steps between the origin of life up the top and complex behavior down the bottom, and said, how often have they evolved on Earth? And the answer is nearly all of them, with a possible exception of oxygenesis, the ability of plants to generate oxygen in our atmosphere. All of them have evolved a number of times independently. And the differences between the different evolutionary paths are quite small. Let me illustrate that with this. This is a bit complicated. Remember me turning chips into more me? In order to do that, I need a complicated program inside me that says what cells should go where, what chemicals should go where. I don't want my eye cells to suddenly say, hey, I think I'm going to be a bit of liver today. Okay? Even things like development of the hand, as an incredibly complex program of hundreds of cell movements, cell development, cell death. So that means a big collection of instructions. That means a big genome, lots of DNA. And we have about 3 billion bases of DNA in us to tell us how to work. We are eukaryotes, organisms with a cell nucleus in which the DNA is kept. And all complex multicellular organisms like plants, fungi, animals are eukaryotes. Compare the bacteria, the prokaryotes. They tend to have much smaller genomes, and their ability to develop complicated multicellular forms is extremely limited. Here's the sizes of the genomes. So this is sequenced genomes. Scientists now sequence the entire DNA in an organism. I think that's just staggeringly cool, but that's another talk. This is the fraction of sequence of genomes, and this was about 6 months ago, so it's out of date already. And this is the logarithm of the size in megabases. I think there should be a game that has megabases in it. Sounds like something large with a club, doesn't it? But in this case, it's just 1 million bases of DNA. The green graph is the eukaryotes, organisms like us. Some of them are quite small, like yeast. Some of them are huge, like you and I. The red ones are the prokaryotes, the bacteria. Some of them overlap with those yeasts, but they never get any bigger. Why not? Is there something hugely different between bacteria and us? And we looked into this in some detail, and the answer actually is not a lot. Nearly all the chemistry that our genes use to control themselves, to control the cells, has analogues or homologues, in other words, things that look the same or things have the same evolutionary origin in bacteria. The one thing that seems to be different is the underlying logic. You know, like it's as if they use HTML and we use C++ or something, or possibly the other way around. But how easy that is to change, we don't know. But it certainly suggests there's not a massive chemical difference, which once you get locked into that, then that's it forever. Here's another example. This has gone pale. This was black yesterday. So this is the evolution of intelligence. And there are a number of different ways that you can describe intelligence. Intelligent organisms, you could say ones that make tools, ones that use tools, ones that play to develop their behavior rather than have it pre-programmed in, ones that have social division of labor. And so we plotted all these on an evolutionary tree. So down here, down the bottom, we have the earliest known multicellular organism, back before the Cambrian, 600 million years ago. And then all the branches are the different lines of descent of life. And up here, we have the primates, then other mammals. Primates have all 4 of these characteristics of intelligence. Other mammals have at least 3. The crows and parrots have 2. Crows are pretty smart. A number of other songbirds show tool use behavior. The social insects show division of labor, which may or may not be a good model for us. And the octopuses. Octopuses are spectacular. They play. They use tools. They might even make tools. They last shared a common ancestor with the primates down here in the Cambrian 500 million years ago. Completely independent evolution of being smart and planning and problem solving and using tools. Dirk and I have actually expanded the 30,000 words of paper into about 80,000 words of book, which is meant to be reasonably accessible, so that should be coming out from Springer fairly soon if you're interested in following up some more of this. It is, I think, a fascinating thought that if you have life on a world, and if that world is habitable for long enough, you will get things, organisms evolving, that are smart. So, if the planet has life, if it's stably habitable, yes, you will get smart, problem-solving, tool-using creatures. Will they communicate with us? That's what SETI was about. The problem with SETI was that Frank Drake said, yeah, there could be between 20 and 50 million communicating civilizations out there. And a number of people said, yeah, 50 million communicating civilizations. And then Enrico Fermi famously said, well, if there's so many of them, where are they? That's called the Fermi paradox. If it's so easy, why isn't there more life out there? Well, so with a lot of unknowns in that. But we don't really mean this. This is a smart animal. This is a communicating animal. This is a tool-using animal. But we're not going to detect this at interstellar different distances. What we're going to detect is this. We're detecting technology. And only humans seem to have evolved technology on Earth. Now, the problem with the SETI agenda is that it was set up in the 50s and early 60s. And at the time, focus of technology was on power, on speed, on big radio dishes, on atom bombs, that sort of thing. And so, naturally, the program looked for those sort of signals of technology on other worlds. Now, those signals are still being radiated into space. If you look at the radio power being put out by Earth, this is total power being pumped up by humanity in watts. Get a logarithmic scale up here, and date along here. This is very rough estimates that I pulled together from several sources. So factor of 10 could well be completely wrong here, but it gives you an idea. So the red line is ballistic missile early warning systems. And during the 50s and 60s, they pumped out enormous amounts of power. That's been dropping off since. The green line, oddly, is radio. Radio power seems to have increased over the last decade or two. And I think mainly because it becomes easier to make radio, to set up a radio station. And you can't get cable in your car yet. The moral of this story is that humans tend to add to technology. They don't throw something away. The radio spectrum is there. Something that David said to me when we were discussing this talk before. The radio spectrum is there. We're going to use it for something. The question is, are we going to use it for something that somebody else, another entity looking at our Earth from far away, will recognize as being technological? Or will to them it just look like noise? And this is the big question about the last of Frank Drake's terms, L. How long does a communicating civilization communicate with us? Part of that is how long we survive, but part of it is how do what we use our technology. Will we recognize it? So, take an example. This is the speed up here. This is top speed of aircraft in kilometers per hour. So this has gone very pale for some reason. 10, 100, 1,000. And this is how the graph would have looked around 1955. And people looking at this in the late 50s and early 60s said this is going up exponentially. Remember, this is a log scale, so a straight line up here is an exponential. By 2001, we'll all be flying to the moon in this. That's not what happened. What happened was it flattened off. There were lots of craft that went faster and faster, but the bulk of them, I've not filled in all the sort of little ones down here. The bulk of them plateaued up. And this, of course, is the plateau there's the speed of sound, which is the technological reason for that. But what we've chosen to do, rather than send 30 people to the moon at 15 times the speed of sound, we've chosen to send 600 people to Marbella at 500 miles an hour. That's fine, but our choices of how we use technology has implications for the signatures that extraterrestrials might see. And their choices of technology have implications for what we might look for. Just illustrate that with a couple of things that I think are very cool. There's a development, has been for some years, but it's now starting to be implemented, to apply biological principles and what we're learning for biology to engineering. So rather than building things in Victorian terms, lots of power, lots of metal, we think, what does life do? This has been applied to computation, so things like neural nets, genetic algorithms, and so on, a direct inspiration from biology, but also increasingly to physical construction. So things like this. This is a little molecular machine. It's just a demonstrator. It's made of half a dozen molecules of DNA that form a triangle like that. And they're so put together that if you change the conditions slightly, they snap together. And the idea is you could trap a drug molecule in the middle there, and it snaps together and ejects the drug molecule when you want to. This has actually been made, okay, and shown it works in the test tube. Here's a larger example. This is a big protein construct, and this has actually been fabricated. And I think that's astonishing. You know, that's the size of a small virus, entirely synthetic. There are even larger ones that have been designed. This is a cage designed from DNA. It's not actually been made, but you could, again, build that, and you could put an entire virus inside it. Starting to think about how we build things in the future using more information-rich technologies, because that's what this needs, a huge amount of information. And rather than how we built things in the past, leads us to think, how will our technological civilization be detectable in the future? Okay, so this is where we are. Back to the Drake equation. We know how fast stars form. We know how many stars have planets. We're getting to get some hints as to how many of those planets could be habitable. We're starting to get some hints that if we have life, would it develop intelligence, meaning the ability to solve problems and do complicated things. We have no idea how often technology evolves. We have no idea how often life evolves. Now, in Elite Dangerous, we assume, you assume that planets form, sport life, and all the rest. We don't. The last one's an interesting question. That is fine. That is completely scientifically respectable. It's just not proven yet. And I just want to finish off with a different question. Do we actually want to know this stuff? And I think the answer to that is yes, we absolutely want to know whether there's life on other worlds. Bacterial life, slime life, I don't care. Is there life there? Because it is a fundamental scientific and social and philosophical importance to know what is our place in the universe. Why are we here? Are we completely unique? Or are there others out there? And similarly, do we want to know if there's smart life, complex life, trees, fungi, dinosaurs out there? Yes, I really want to know that because that tells something about our evolution and our origins. Do we want to meet and find and know about technological intelligence out there? That's a question for you. Thank you.
And absolutely amazing, William. Good. So a huge round of applause, please, for William Baines. Absolutely amazing. I'm sure that you guys probably have hundreds of questions out there. Some hopefully not quite as dense and serious as is there alien life out there, but some maybe smaller questions. So if you do have questions, please put your hands up in the air for us to see. Lots of questions over here. We do have two roaming mics, one on this side, one on this side. Perhaps this gentleman here on the left-hand side, near Zach. Yes, if you could please stand up, when you ask a question. Thanks.
Hi there. I've heard a theory that the reason scientists think that humans are intelligent is because we respire oxygen, because it's such an unstable gas. Do you think there are any other gases that might affect life, or any gases with the potential to make intelligent life rather than just sort of single cellular organisms that don't really go from there?
Yeah, really good question. You recall I talked about oxygenesis and that being one of the steps, and we weren't sure about that. That is exactly the reason for that being a key innovation, because there's this hypothesis that very active animal life, and particularly intelligent animal life, needs oxygen, because the reaction of food with oxygen releases lots of energy, and very few other reactions produce that amount, that density of energy. And there are two answers. The direct answer to your question is no. The obvious other gases to use in that sort of chemistry would be fluorine or chlorine, and both of those, if you had an atmosphere of those around the planet, it would then immediately eat the planet. So that, it would just react with all the rocks, and that would be gone. Oxygen's very unusual in that. I'm not completely convinced that that argument is right, and again, watch this space for that, because Dirk Schultz-McCook and I are putting some ideas together on that. But I think there are other ways to get lots of energy, and I don't think being intelligent needs as much energy as we might think it does. So a non-oxygenic intelligent life form might not leap and wave its arms around quite as much as I do, but I think it's still possible. But really, really interesting question, and that's still a research topic.
Fantastic. Any questions maybe from over here? Any? Oh, yep, right here in the middle. Sorry, the microphone's coming to you.
Do you think it's more likely that the simple molecules jump into life, become life? Is that more likely than, say, that simple life developing intelligence?
So we've no idea how the simple molecules organize themselves and build themselves into the more complicated ones that could then replicate themselves. So how origin of life happened. So it's really hard to say, is that more likely than the next step, which is that very simple life becoming more complex? My gut feel is no, that there's something quite complicated and unlikely happening in that origin of life step from simple to complicated. I fudge that slightly because clearly if you mix up a load of simple molecules and just cook them up for a long time, what you get is brown goo. Okay, you don't get life. So there has to be other inputs. There has to be energy. There has to be nonlinear dynamics. There has to be all sorts of stuff going on. And what those are is not entirely clear, but it's not just a straight simple to complicated. But I think that is a fairly unlikely step. I think once you've got life, developing more complex life is reasonably likely.
Okay, I think we have a question. Time for two more, perhaps over here in the middle on the left-hand side. If you could stand up, please, sir. Thank you.
Going back to the detection of life, do you think it's more likely that we're going to find, well, the first finding of alternative life is going to be in our own solar system, like on Mars or Europa, or are we more likely to find life, sort of exoplanetary life, through atmosphere detection? which do you think would be first?
Wow.
An easy one to answer this.
Yeah.
Finally.
So, how long have we got? My prediction, and this is going to go on YouTube, so somebody better look back at it. My prediction is we will find life on Mars. Quite apart from the contamination we've landed there on our various landers. And I think that is because Mars life will be contaminated from Earth, or Earth life from Mars, or we will not be able to tell whether that's happened or not. So, Mars is so easy to get to. I mean, it's just a walk down the block compared to going to, Proxima. There'll be more landers, there'll be more experiments. I think we will find life on Mars. I think it's going to be incredibly hard to say whether that's independent. Finding life around extrasolar planets, I think, is going to be, remember the big telescope curve up here? I think it's going to be towards the end of that, because I think that's going to be harder than people think, or harder than the optimists hope, let's say, put it like that. And if you don't find anything, what does that prove? There's some really interesting models that show that if you'd used the modern techniques to look at Earth 3 billion years ago, you would not have found life on Earth. Earth because clearly had life on it. So, yeah.
You ask hard questions, you're going to get hard answers, all right? One more question perhaps from this side of the room over here. Oh, yeah, just this gentleman right at the back. Right.
Yep.
Or even the person, standing at the back, that one. Yeah, great. Thank you.
Hi, I wondered if this is an information science problem. It's about how you represent the information and go from information to function. Do you see any alternatives to the 4 bases of DNA?
Goodness. Well, I know some information scientists who would have very strong views on that. Are there alternatives to 4 bases of DNA? Yes, because you can build DNA with different bases in. That's the sort of trivial version. Is there an alternative to DNA as an information coding system? Maybe. Some chemists will say no, it is the optimal and pretty much the only one that'll work. Others will say that's obviously nonsense. But that's the sort of chemical information, chemical implementation of the control system. I think there is something very interesting in the information theory analysis of living systems. And there's a professor in the University of Arizona called Sarah Walker who's looking at not the particular gases in an atmosphere, but the network of how those gases interact, and has life perturbed that? The network of metabolism and how the information flows around that. I think that's a very interesting area of research. The problem is, how do you detect very sophisticated information flows at a distance of 10 parsecs, when all you could see is a few blips on a spectrogram? So at the moment, we're looking for chemistry. But information is clearly at the core of life. It is that code. It's that thing that says a William should look like a William and not like a tree or a mushroom. That's about information. And yes, that has to be core to what life is.
Fascinating stuff. I think that's kind of all we have time for with questions. I have one last question, actually. Because obviously that was all very simple, and I found it all very easy to understand.
Of course, yes.
But if people do want to find out some more information or see talks from yourself, where can people go to actually find any more information about that kind of thing? Do you have an email or a website?
I think the simplest thing to do is I'm going to be milling around afterwards, so just come and grab me.
Fantastic.
No more than 4 at a time, please.
There you go. So one last time, absolutely fascinating talk. Thank you so much. A huge round of applause for William Baines, please.